Greetings, everybody. Learning is a hobby here. In this video, I want to go over the solutions to chapter 28 exercise set in the book Calculus by Michael Spivak. So that's what I'm going to do here. Let me bring up my solutions, and then we'll go over them. Okay, so there are a bunch of problems here that are a bit repetitive because there's a number of these that just ask to show that a certain set with two binary operations form a field or whether they don't form a field. So the first question is kind of like that. We did some examples like this in the chapter itself. So I didn't really do fully all of the problems like this, except for the last two in the exercise set, because those are like the more involved ones. So the other ones that are in this section, I kind of just hand waved a little bit, but I explained how to do it if you want to do it. I just didn't feel like going through all of the tedious work of just writing it all out. So, but anyway, let me read the problem here instead of telling you what I did. So, question number one says this. Let F be the set 0, 1, 2, and define operations plus and times on F by the following tables. And then here, if you're familiar with modular arithmetic, this is just the integers modulo 3, basically. Addition modulo 3 and multiplication modulo 3. All right, and Spivak wants us to show that this set with those two operations defined by those operation tables is a field and prove that it cannot be made into an ordered field. So this is one of those questions that I kind of just gave short shrift to because I didn't feel like writing out all of the work for it. So, but I'll explain quickly how you could do it if you did want to. So, property 2, 3, 5, 6 are virtually apparent, visually apparent from the tables above. Let me just show you what I mean. For example, if you go to the addition table, notice that notice that the this table here is symmetric through I don't want to actually write on this, but is symmetric through the diagonal. That shows that addition is commutative. If you want to show that uh, what else? That addition has an additive identity, then you could see that from the table here. For example, 0, when you add to any element of the set, you get the same element back. Also, you could see that there are additive inverses, right? There are, for each number, there's a number that you add to it that gives you the additive identity, right? Similar thing for the multiplication table. You can see that there is a multiplicative identity. You can see that multiplication commutes because the table is symmetric through the diagonal here. And you can see that each non-zero element has a multiplicative inverse, right? And then property 1, 4, 7 are inherited from the integers. If you know about the integers modulo some natural number n, then you know how this works. So, for example, a times in parentheses b plus c is congruent to a times b plus a times c mod 3, and same thing for these other operations here. So if you know about those types of operations, then you can actually write out the proofs in detail if you want to. I just didn't feel like going through the work for that because it's straightforward and just kind of at this point it kind of feels like busy work to me. So, but if this is your first time seeing fields and so on, you probably should work out all of the details. But anyway, and then the second part of the question. So anyway, that shows that it's a field. The second part of the question is to show that it can't form. Sorry, it cannot be made into an ordered field. And here's my proof of that. So F cannot be made into an ordered field, since if you assume that one is a positive number, then 1 plus 1 equals 2 by the addition table. So that means that 2 is also a positive number. Then 1 plus 2 is 0, by the addition table, which means that 0 would be a positive number, and that contradicts property number 8 of the three order axioms that we had. Similarly, if 2 is a positive number, then 2 plus 2 equals 1. Again, you could just look at the addition table for that, which means 1 is in the positive numbers, and we get the same contradiction. So there's no way for this set to be made into an ordered field. Okay, question number 2 is very similar. Suppose now that we try to construct a field F having 0, 1, 2, 3 with operations plus and multiplies as defined in the table below. Show that F will not be a field. Actually, this one is a lot simpler because you just have to show that at least one of the axioms is not satisfied. And this one is just the one line proof. So two, for example, if you look at the multiplication table, the element 2 has no multiplicative inverse. So that shows that this is not a field. All right. Question number 3 is similar to question number 1. Let F be the set 0 with elements 0, 1, alpha, beta, and define operations plus and times on F by the following tables. These are the tables. And again, this is a very straightforward thing. You just show that all the axioms are satisfied. Again, property 2, 3, 5, 6 are just visually apparent from the tables. You can see that they're satisfied. The other ones you can, do this like we did in the chapter when we showed that Z modulo 2 was a field, with addition and multiplication modulo 2. Here, whoops, hold on the headphones. Let me just make sure that the audio is still going. Okay. Um, there is an easier way of doing this if you know some abstract algebra, but that's not assumed in Spivak's book. So I just did it the sort of the brute force way here. Although, I didn't feel like working out all of the examples because there's a number of them to do in each of the cases that are not apparent from the tables, like the associativity and distributivity and so on. So, but anyway, this is like how you would do them, right? You just show that the axioms are satisfied by all combinations of the elements. Okay. Question number 4. Let me just move something out of the way. Okay. Question number 4, there's two parts to this. Part A says, let F be a field in which 1 plus 1 is 0. And we want to show that A plus A equals 0 for all A. And this can also be written as A equals minus A. There's a one-line proof for this. So here's my proof. A plus A is A times 1 plus A times 1, which equals A, you can factor out the A by the distributive law, equals A times 1 plus 1, which is A times 0, which is 0. And that shows that when you sum any element of the field with itself, you get 0. Part B says, suppose that A plus A equals 0 for some A not 0. Show that 1 plus 1 equals 0, and consequently B plus B equals 0 for all B. So here's my proof. So 0 equals A plus A is equal to A times 1 plus A times 1, which is, again, by the distributive law, you can factor out the A, which gives you A times 1 plus 1. Since A is not 0, there is A inverse in F such that 0 is equal to A inverse times 0, which is equal to A inverse times A times 1 plus 1, which by the associativity law is equal to A inverse times A times 1 plus 1, or in other words, 1 times 1 plus 1 is equal to 1 plus 1, which shows that 1 plus 1 equals 0. Okay, question number 5. I think there's two parts to this one as well. Part A says, show that in any field we have the sum of 1 with itself m times the sum of n with itself n times is equal to the sum of 1 with itself m times n times for all natural numbers m and n. Okay, I did this by induction. So let m be a fixed natural number. We induct on the number n. So here's the base step. So if we take 1 summed with itself m times the number 1, we get m times 1. 1 plus itself m times, because when you multiply anything by 1, it doesn't change the value, right? 1 is the multiplicative identity. Right, then we move on to the inductive step. So assume that the property is true for some n in some natural number n, and consider the sum of 1 with itself m times the sum of 1 with itself n plus 1 times. Then by associativity of addition, that's equal to the sum of the sum of 1 with itself m times in parentheses the sum of 1 with itself n times plus 1, and then by the distributive law we can distribute the sum of 1 with itself m times over the addition here, and that gives us this expression here. And then when we use the inductive hypothesis, the first part here is equal to this, and then this is just the sum of one with itself m times because we're multiplying by the multiplicative identity. That gives us the sum of one with itself m times n plus m times, which again is equal to m times n plus 1. Therefore, the property holds for all natural numbers. All right. Part B, suppose that in a field F, we have 1 plus 1, with itself m times equals 0 for some natural number m. Show that the smallest m with this property must be a prime number. This prime number is called the characteristic of F. Here's my proof. Assume for the sake of contradiction that m is composite. Then there are a, b in the natural numbers n, such that ab less than m and m equals ab. Then the sum of one with itself m times equals 0 implies that the sum of the sum of one with itself a times the sum of one with itself b times is equal to the sum of one with itself m times, which is equal to 0. And this contradicts that m is the smallest number where the sum of one with itself is equal to, some number of times is equal to 0. Therefore, m must be prime. All right, question number 6. Let F be any field with only finitely many elements. Part A, show that there must be distinct natural numbers m and n with the sum of one with itself m times equals the sum of one with itself n times. Here's the proof. Let F be a finite field. So in other words, the cardinality of the set F is not infinity, right? It's finite. Assume for the sake of contradiction that no natural numbers n m exist for which that property holds, then any sum of one with itself will be a unique element of F. However, this contradicts that the cardinality of F is finite. Therefore, two such integers must exist. Right, so proof by contradiction. Part B, conclude that there's some natural number k with the sum of one with itself k times equals 0. So again, if we assume that F is finite, then and that that the property in part A holds for some n and m, and that n is less than m, then the sum of one with itself m times plus the sum of negative one with itself n times is equal to 0. That implies that the sum of one with itself m minus n times is equal to 0, since nm is an element of n, and m minus n is positive, therefore m minus n is a natural number. Therefore, there is some natural number that for which, when you take the sum of one with itself that many times, gives you the additive identity, the 0 element. Okay, question number 7. Let A, B, C, and D be elements of a field F with AD minus BC not 0. Show that for any alpha, beta in F, the equations, so here we have a linear system and two unknowns, A times X plus B times Y equals alpha, and CX plus DY equals beta can be solved for X and Y in F. And this is a pretty easy proof. You just show that it works. So, for example, if you use the addition method that you learn for solving systems of equations, it works here because all the field axioms are satisfied. So when we do that, we end up with X equaling this number here, B times beta minus D times alpha over AD minus BC. We are guaranteed that that's a number because AD minus BC is not 0, right? And then you do a similar thing to solve for Y, and you get a number again because AD minus BC is not 0. Okay, question number 8. Let A be an element of a field F. A square root in quotes of A is an element B of F with B squared equals B times B equals A. And there's multiple parts here. Part A says how many square roots does 0 have? So in order to do this, I had to use make some lemmas because we haven't really talked too much about other properties of fields. And actually, I probably should have done another lemma here, but I'll just state it because I've proved this in other parts, in other areas. So, for example, maybe I'll just call this lemma 0. Um, Additive identities and inverses are unique. So I didn't actually prove these here, so I'll just assume that those things hold. But you could easily prove it's like a one-line proof. Like I said, I've done that proof in other videos, so I'll just skip that. But anyway, you need to have some lemmas. So for example, you need to know that alpha for any alpha in F, then alpha times 0 is 0. And this is the proof. Again, I've done this one in other places as well too, so I won't belabor it. But you can see my proof here if you like. Um, so then Oh, here we go. And then the proof of the actual statement that they're asking us to show, which is how many, sorry, not the proof, the solution for how many square roots zero has. Going down here, assume that alpha times alpha is zero and alpha is not zero. Then alpha inverse is an element of F, and alpha times alpha inverse is zero times alpha inverse, and alpha times, just using the associative law, right? Alpha times in parentheses alpha times alpha inverse is zero by lemma one, and by the associative law also for the left-hand side. Alpha times 1 is equal to 0, which implies that alpha is 0, which contradicts that alpha is not 0. Therefore, the only square root um, of 0 is 0. So there's only one square root of 0. Okay, part B, suppose that alpha is not 0. Show that if A has a square root, then it has two square roots unless 1 plus 1 is 0, in which case A has only 1. All right. Again, you need some lemmas here. I'll just read out the lemmas and you can pause your screen if you want to see the proofs. I've done these proofs in other places before, so I won't belabor them. But we do need these facts, and it's not proved. These things aren't proved in the section in chapter 28. So lemma two here that I have stated is let alpha be an element of the field, then alpha times negative one is negative alpha. And then you can see the proof here. Like I said, I've done this like I feel like several times already on the channel, so I'm not going to belabor it. Lemma three, negative alpha is alpha times alpha for all alpha in F. And again, you can see my proof here, right? And then the proof of the actual statement, just to remind you what it is show that if A is non-zero, and it has, sorry, if alpha is non-zero, show that, oh, is this a typo? Hold on. Show that if A has a square root, then it has two square roots. This should be a, let's see, did I use alpha in the proof? This should be A here. Okay, so now that we fixed that, here's my proof. So if alpha times alpha is A, then negative alpha times negative alpha is alpha times alpha, which is equal to A. Therefore, if alpha is not zero, then plus minus alpha are square roots of A. Furthermore, alpha not negative alpha by trichotomy. If one plus one equals zero, so that proves the statement. But if then here's that caveat. If one plus one equals zero in F, then by 4A, alpha equals negative alpha for any alpha in F. Therefore, square roots are unique in such a field. Okay, question number 9. Part A, consider an equation x squared plus bx plus c equals 0, where b and c are elements of a field F. Suppose that b squared minus 4 times c has a square root r in F. Show that minus b plus r over 2 is a solution of this equation. Here he's just stating, because we're working in an abstract field here, what the number 2 means here is 1 plus 1, so the sum of the additive identity with itself. And 4 means uh, 2 plus 2, or in other words, the sum of the additive identity with itself 4 times, if you want to think about it like that. So here's the proof. It's just completing the process of completing the square. That process works in a field not of characteristic 2, which we'll handle in a second. But x squared plus bx plus 2 inverse times b all squared equals 2 inverse times b squared minus c. And you just go through the process. Hopefully you guys remember completing the square from your algebra courses. It's the same thing here, except we're dealing with elements of some arbitrary field. These are not necessarily real numbers or complex numbers. All right, and also I'm writing 2 to the minus 1, because 2 to the minus 1 here may not actually be the number 1/2. So um, when you do take the square root of these two things here, you get that x plus 2 inverse times b is 2 inverse times r. Remember, we said that the square root of b squared minus 2 squared times c is, which is, b squared minus 4 times c is r. All right. That gives you that, when you solve for x equals negative 2 inverse times b plus 2 inverse times r, or in other words, 2 inverse times negative b plus r, which is what they wanted us to show. Right. And then now in part B, we handle the problem that comes up when you have a field of characteristic 2. So in the field F2 of the text, both elements clearly have a square root. On the other hand, excuse me, on the other hand, it is easy to check that neither element satisfies the equation x squared plus x plus 1 equals 0. Thus, some detail in part A must be incorrect. What is it? We assumed that we were in a field of characteristic not two, or in other words, we assumed that 1 plus 1 was not 0. Okay, question number 10. Let F be a field and A an element of F, which does not have a square root. This problem shows how to construct a bigger field, F prime, containing F, in which A does have a square root. This construction has already been carried through in a special case, namely F equals R and A equals -1. This special case should guide you through this example. When Spivak says that, he's referring to previous chapters in the textbook that we haven't gotten up to yet. So when we get to the chapter that deals with complex numbers, I'm sure we'll do that in those sections. Anyhow, let F prime consist of all pairs x, y with x and y in F. If the operations on F are plus and times, define operations um, plus with a circle around it and times with a circle around it. I'll just call it plus and times here, just so the language doesn't become too complicated. On F prime as follows. So xy plus 2 zw is equal to x plus z, y plus w, and xy times zw equals xz plus ayw, comma, yz plus xw. And in part A, Spivak wants us to prove that F prime with those operations is a field. And I went through, this is one that I went through the, all the properties in detail. So you can see them here. Um, I'll just scroll through and you can pause if you want to, because this is very straightforward and really not complicated at all. It's just tedious. However, I should mention, if you don't feel like pausing your screen, um, something I've done recently is I restarted my Patreon page, and all of the PDFs of the chapter summaries and the solutions are available there to download as PDFs if you're interested in that. So if you go to the Patreon page, you have to join. It's $3 to join, but then you can download all of my PDFs of solutions and lecture notes for not lecture notes, some chapter summaries for all the math videos that I've done on the channel. So if you'd rather do that instead, that's available. But anyway, I'll just scroll through this slowly so you can pause your screen if you want to see it. I'm not going to read all of this out. Right. Again, you just show that the properties satisfy, um, you know, the um, the field axioms. The only real complicated part here is figuring out what the multiplicative identity is and what the multiplicative inverses are. But they follow the same pattern as they do for the imaginary unit. Uh, when you addend the imaginary unit. In other words, when you form the complex numbers, you get this. So um, that's question 10 part A, and then part B says prove that x comma 0 plus y comma 0 is x plus y comma 0, and x comma 0 times y comma 0 is xy comma 0, so that we may agree to abbreviate x comma 0 by x. And again, this is straightforward. You just show that it works by using the multiplication and addition properties. Right. And then finally, part C, find a square root of A equals A comma 0 in F prime. Right. And you'll find that the solution that works is 0 comma 1, just like it works for the square root of -1 and, when you construct the complex numbers. So here I'm just demonstrating that. So 0, 1 is the square root of A comma 0 in that field. Okay, last question for this section, question 11, and this is kind of a long one. Let F be the set of all four tuples W, X, Y, Z of real numbers defined plus and times by these properties here. I'm not going to read these out. I'll show you why in a second. Part A asks us to show that F satisfies all conditions for a field except number 6, meaning show that all the properties of a field are satisfied by this set with those binary operations, except for addition is not commutative. Um, at times, the algebra will become quite ornate, but the existence of multiplicative inverses is the only point requiring any thought. So, let me just show you how I handle this, because if you you could totally do this using the way that he defines the operations here, but I guarantee if you try to do this using the operations as they're formulated here in terms of components of the four tuples here, you're going to want to slit your wrists. It's going to be just not a fun exercise. And I want to show you how I did it because this set is a special set of numbers. They're called the quaternions. And if you've taken linear algebra or abstract algebra, you might be familiar with an easier way of writing down these operations on the quaternions if you know just a little bit about vector notation. So let me just show you because that's the way I did it. I didn't feel like writing out 10 pages of x times u minus v, I didn't feel like doing that. So, but you'll see even with the vector notation, still gets kind of a bit hairy here. So here's my proof. If you know just a bit about of linear algebra, this problem is light years easier and gives more insight into what's going on. So here, let ijk be the usual orthonormal basis in R3. Then we'll define the four tuple w, x, y, z with w plus p hat, where w is the real number w, and p hat is the vector xi plus yj plus zk, where ijk are uh, the ordinary unit vectors. Um, it's a little bit more complicated. They're not sitting in R3. They're actually sitting in R4, but I would be like 0, 1, 0, 0. J would be 0, 0, 1, 0, 0, 1, 0, and K would be 0, 0, 0, 1, if that makes sense. All right. If we do this, then it's easier to write down the operations like this. So, for example, W plus this vector P hat plus S plus this vector Q hat is just W plus S plus P hat plus Q hat, right? And multiplication still looks very complicated, but it's a lot easier to handle than if you write things out the way that he has it here, just in terms of the components. So let me just describe this here. And this is an interesting thing about the quaternions is that all the major vector space operations actually show up in the product for quaternions. So for example, if you want to multiply W plus P hat times S times Q hat, it's equal to WS minus P hat dot product with Q hat plus the scalar product of W with Q hat plus the scalar product of S with P hat plus the cross product of P hat and Q hat. So if you notice, you get WS is a product of two scalars. Here we have the dot product. Here we have scalar product, or scalar multiplication, and here we have the cross product. So these operations all show up just in the product structure of the quaternions. Anyway, we also have a notion of a conjugate. So if you want to take the conjugate of W plus P hat, you just negate the vector part. So you negate P hat. So the conjugate of W plus P hat is W minus P hat. And there's a similar property here. When you multiply conjugates together, what you get is the norm of the quaternion W plus P hat. So if you multiply W plus P hat by W minus P hat over the norm of W plus P hat squared, you get 1. So in other words, this number here is the multiplicative inverse of that quaternion. So this element here is W plus P hat inverse. Right? And notice that it itself is still a quaternion. So, okay, so using these rules, we can show that the field axioms, barring number 6, all are satisfied by this set with those operations. So here we can show that addition. I'm not going to belabor it. Again, you can pause your screen if you want to see that, but I'll just show you. Here you can see that addition is associative. Here, the quaternion 0 plus 0 hat is the additive identity for the set. If you have a quaternion W plus P hat, the additive inverse of that is minus W minus P hat, which you can check here. Then we have also notice that quaternion addition is commutative. Number 4, we're going to show that quaternion multiplication is associative. This is the most tedious of them, I think. So what I did was I just did it in this order first, and then I did it in, where did I write it? Then I did it in this order second, and you can see that the two things are equal to each other just by doing some rearrangements, which I didn't bother to write down just because I didn't I didn't feel like doing it. So here, just if you compare this with this, you'll see that they're both the same quaternion. Okay, number five. Here, um, one plus zero hat acts as the multiplicative identity, and again, like I said, W minus P hat over the norm of P hat squared. Sorry, this should be the norm of W plus P hat squared. That's a typo. Let me just fix that. Okay, and clearly you can see that that's equal to one. All right, now here's one of the important parts of this problem, which is that multiplication doesn't commute in this set. So the quaternions are an example of a non-commutative ring. Right, so here, if you take I times j in this set, you get the cross product I times j, which you can see I did the multiplication out here. What you end up with is I times j. But notice if you switch the order, j times I, you get j times so you get the cross product of j with I. And remember the cross product, if you know about the cross product, that's not a commutative operation. When you swap the elements, the factors, you get the negative of it doing the cross product in the opposite direction. So notice that ij here is not the same quaternion as j times I. So therefore, multiplication is not commutative in this set. All right, and then distributivity also is satisfied here. You can just pause your screen if you want to see that. Or you can go to the Patreon page and download the document. Okay, so this forms we can't say it's a field because it doesn't satisfy axiom 6, but it forms a non-commutative ring. All right, now part B, it's customary to denote the fourth tuple 0, 1, 0, 0 by I, 0, 0, 1, 0 by J. This is what I was saying before, and 0, 0, 0, 1 by K. Find all 9 products of pairs I, J, and K. The results will show in particular that condition 6 is definitely false. This skew field F is known as the quaternions. All right, and then you just do the calculations. So here they are. This is what I not only did the products of the pairs, but I also did the product of the three vectors with themselves too. You only get two distinct answers in that case. So yeah, so that's chapter 28, the solutions. Let me stop my screen share. Okay, now we do have coming coming up in the next video in this series, chapter 29, which is a long one, but it's an important one. In the next chapter, we're going to construct the real numbers now using Dedekind cuts rather than like we did in Tau, where we used Cauchy sequences. So this one is going to be a long video when I get around to it. I haven't even started out writing up my summary of the chapter yet, but hopefully sometime this week that'll get posted. I want to try and shoot to getting the epilogue for Spivak done before the end of the year, so before New Year, so that in the new year we can start back, at the beginning of. Sorry, not in the beginning. Start back in chapter 9 in Spivak, and we can do all the stuff on derivatives, integrals, and sequences and series and so on. All right, guys. Give me a like and subscribe down below if you enjoy these videos or if you get something out of them. And again, if you want to check out the Patreon page, that stuff is there. It's $3 a month. And I'm going to I've posted all of the previous lecture notes and the previous solutions there that you can download as a PDF. And going forward, I'm always going to be posting new those whatever I have when on the math videos when I'm showing you my notes or my solutions, that stuff will always get posted to the Patreon page. It'll be downloadable for you if you're a member. Okay. So I'll see you guys in the next one. I hope you guys are enjoying my 12 Days of Christmas videos, and I'll see you next time.